Linear approximation in uncertainty propagation uses the first-order Taylor expansion to estimate how uncertainties in input quantities affect the uncertainty in a result. You take the derivative of the function with respect to each input, multiply each derivative by the input uncertainty, and combine those contributions, which is valid when uncertainties are small compared to the values. Imagine you have a recipe, and one ingredient amount might be a little off. Linear approximation treats the function that turns ingredients into the final dish as if it were a straight line near your best guess. So small changes produce predictable, proportional changes in the result. You compute how sensitive the result is to each ingredient by finding the slope or derivative with respect to that ingredient, multiply that slope by the size of the possible error for that ingredient, and those products tell you how much each error moves the result. If errors are independent, you usually combine those individual contributions by adding their squares and then taking the square root to get the overall uncertainty, because positive and negative deviations can cancel less often than add up in a root mean square sense. This method assumes the uncertainties are small, so the curved parts of the function do not bend the straight line approximation too much. A common mistake is applying linear approximation when uncertainties are not small, which can give seriously wrong results. So check the relative size of uncertainties and use higher order terms or numerical propagation if errors are large. Another error is forgetting correlations between inputs. If two inputs change together, their contributions do not combine by simple root sum square, and you must include covariance terms, so estimate or measure correlations when they are likely. People also sometimes ignore units and dimensional consistency when taking derivatives, which leads to arithmetic mistakes, so keep units clear and manipulate symbols before plugging in numbers. For more examples, worked corrections, and video explanations about uncertainty, propagation, and linear approximation, visit www.gumballdegree.com to find more videos and resources.